Okay, so hi, I'm Will. I'm a platform engineer at Pusher, and we've been spending the past year using Haskell to implement a new message bus. So when I was coming up with this talk, I was thinking it would be more of a general experience report, looking at the pros and cons of using the language, but I ended up focusing more and more on one particular topic, which was our experience with problems with the garbage collector for our particular use case. And I just think that's a bit more of an interesting topic. So it's more of a deep dive into an overview of the garbage collector and why the design decisions for it are a problem for our particular use case. And then also looking at some alternative approaches that might be potentially solve our issue. So just to get started, I'll just explain what we do because it's quite important for this particular piece of software. So we're a hosted WebSockets API. So if it basically allows our customers to send a message and then it gets broadcasted to all their connected clients via WebSockets. So it's a PubSub API. And the core of the system is based around Redis PubSub, which is really great. It's fast and doesn't cause us too many issues. But there's one big problem with it, and it's basically that if a client disconnects for a short period of time, particularly if they're on a mobile device and they go under a bridge or something, then they'll miss all the messages during that period of time. And it's actually a problem that a lot of our customers have to implement themselves. So we kind of want to solve that problem for them. So it basically means that we want to keep almost like a cache of messages around. We chose to do this for 5 minutes because we think that will cover most sort of transient disconnections and also be affordable for us in terms of memory usage. But the problem is now that we're storing this, so previously it was completely stateless, our system, except for some configuration and so on. We now need to make sure that if there's any kind of system failure, if there's a failover, we can failover to a new node that has an up-to-date state. So that's basically the problem that the system's trying to solve. And that's just going over that again. The kind of key point is that the performance is quite important to us, or very important to us actually. So we want it to handle about 10,000 publishes a second. But the main thing is we want to keep the latency low at that volume. And there's the middle point there. So we actually picked Raft to do the distributed consensus, so providing this durability guarantee. And that was actually something I was going to talk more about because there's currently no Raft libraries in Haskell, and we spent a long time trying to implement that ourselves. And yeah, it's a big topic, and it might be something for another talk. So we're going to focus on other things. Oh, sorry. And you're probably wondering why we chose Haskell in the first place. The decision was actually made before I started working there, so I can't say too much about it. But it was actually one of the reasons I was quite keen on joining the company, is that they were a lot of what made people in the company interested in Haskell, the sort of interest in the same philosophy that underlies Haskell, I think resonated with them and also me. So yeah, things that I mentioned there really, the strong static type system, the general functional programming style. And the last point, something that I really like, is when a language is based on some simple first principles and then everything else comes from that, as opposed to just being special cases. And I should mention, probably the main reason is the team had already experimented with Haskell and had a couple of small production systems written in it. So they had trialed it previously. And the other thing is that it's fast, or we had heard that it's fast, which is obviously important for us. So I'm just going to quickly go over just some things we liked and disliked. It's probably things you've heard before, but I just thought it's interesting to hear another data point reiterating these things. So like I said before, the types system was really, really great for us. With most of our systems written in Ruby, it's quite a 5-year-old system, quite large now, and I think a lot of the team were getting pretty tired of that. So not only was it good for correctness, but also like designing the system in the first place, we found really good. So concurrency obviously was really nice. We have a lot of like a highly concurrent system, and it's really nice just to be able to start threads without worrying too much about the cost of that. And STM's just really amazing in terms of composing these, creating atomic transactions via composition of smaller things. Tooling was really useful, particularly when we're doing the performance investigations, which kind of surprised me. I think of Haskell as, I think its reputation as a more academic language makes people think that the tooling isn't great, and there are problems with it, but I was surprised how good things like thread scope were once you managed to get it set up and figure out how to use it. Also, halfway through our development, we started using Stack, which was really great for us. It's got some issues, but in general, it was a lot better experience than previously we had. And yeah, also hiring was really great. So we found it really easy to get involved in the community by doing things like this, and also writing blog posts. There's a lot of engagement from people who were very high quality, and a lot of them were potentially interested in applying for jobs at our company. So that's just a very sort of brief overview. So now some things we disliked, a little bit more detail now. So this is kind of a problem that is probably a downside of it being a fairly simple but general underlying language, is that a lot of things that you'd normally have built into the language or the standard library are implemented as libraries. So it leads to quite a nice approach where it's sort of a Darwinian model for figuring out the best way of doing things, but at the same time there's a lot of competing options, and it's not clear when you start. I mean, there's things that as you use Haskell more and more, you know that you should use text instead of strings, but it's not obvious to beginners. And then there's other things like, I put pipes versus conduit there, but it's not, there's not one that's clearly better than the other, and it means that if you switch projects, it can be quite painful. I just kind of picked on Lens a bit here, but it's basically another symptom of this sort of general language thing where the features are libraries that, particularly for type errors, very quickly the abstractions start to leak. Like Lens conceptually isn't too complicated, but because it's based on all these layers of abstraction, when you get type errors, they're really hard to figure out. So I said tooling is good, but at the same time, there's also, it can sometimes be a little bit clunky to set up, and you've got to build it yourself, and just for newcomers, it can be a bit intimidating, really. The last point there, we found that there's a lot of good tools like Criterion in particular for benchmarking like average running times of a function, but not so much stuff in terms of figuring out worst case latencies, which is what we were mainly worried about. So now we come on to the garbage collection problems that I mentioned earlier, and they're specifically to do with this storage part of our system, so this 5-minute store. So this is just roughly describing what it is. It's a little bit more complicated than this, but you can just think of it as a buffer of messages where messages are constantly being inserted and also being expired from it as well. We quickly found that there was, so we had a distributed benchmarker which tested like a real world, simulated a real world run of the system. We saw these occasional latency spikes in the latency graph, and we opened ThreadScope up, and I don't know how many people are familiar with ThreadScope, but basically it's just showing it's showing like the CPU utilization from one run of an application. So the green part is where the actual application code's running, and the height of that is the CPU usage. And then the orange parts are where the garbage collector's running. And there's actually lots of little ones going on constantly, and then you occasionally get these big pauses. And I'm going to go into sort of our investigation of that and why this is happening. So one of my colleagues, James Fisher, spent some time. So it can be quite hard when you get something like that to figure out exactly what is the root cause of it. And he did some really good work on reducing it to the minimal test case, which basically turned out to be just a simple data.map where you insert and delete at the same rate. And he wrote up a good blog post about his investigation into that. And this is basically the result of the investigation, is that the maximum pause time is proportional to the size of the live set, the working set. So it's not something like the rate of allocations or the rate of garbage or unreferencing of objects. And we only cared about the down here, but we've tested with much larger numbers just so you can really obviously see the pauses. That's in seconds there, so that's like way higher than we could deal with our 50 millisecond requirement. So yeah, that's just reiterating that point. So yeah, we reached out on Stack Overflow, and Simon Marlowe said, yeah, this is going to be a problem, and there's not a huge amount you can do about it. But I thought it would be interesting to look at the sort of trade-offs that have been made in the garbage collector. I should point out I'm by no means an expert in this. I've just understand the very high level of the characteristics of it. So I'm just going to go over those and show why our particular use case, this message store, is the worst case for the garbage collector in terms of the latencies. So yeah, I wasn't sure what to call this. So unreferencing, I basically mean like the rate that objects are dereferenced, but dereferencing can mean something very different. So I'm calling it unreferencing here. So because Haskell's data by default is immutable in Haskell, you create a lot of garbage. So the proportion of live objects to the amount of garbage that's being created is quite high. So these are assumptions that the garbage collector is making about like real world Haskell applications. Yeah, it also assumes that most objects die young, and this is true of pretty much any program, but particularly for the same reason, the immutable data, it happens more frequently in Haskell. So it basically assumes you've got a large amount of very short-lived objects, and then some objects which are going to hang around for a much longer time, possibly for the entire run of the application for some of them. And the other design goal is it tends to favor throughput over latency, and this seems to be a more arbitrary thing, and you often trade off one, generally need to trade off one for the other. So based on those assumptions, it's trying to be as optimal as possible for these particular types of programs. So the garbage collector is copying. Actually, before I show the slide, I should probably show this because it demonstrates it much more clearly. It's a copying garbage collector, so it splits the heap into two, and every garbage collection run, it will do a traversal of all the live objects, and for each one, it will copy it into an inactive heap, and then basically rewrite all the pointers when it does that. So this is really good because it's only the running time of each collection is only proportional to the live objects. So it literally doesn't care about the amount of garbage that's there for each run of the garbage collector. And it's also simple to, I mean, the implementation is much more complicated than I'm just describing, but it does help avoid issues like fragmentation when you just copy stuff along, you're not doing it in place. It's also generational, which is basically an optimization on this. So the heap is split into multiple heaps. Each one's a different generation. And the idea is that when an object survives a certain number of garbage collections, it's moved to a different heap. And the point of this is that for those, basically for the objects which are long-lived and are going to survive a large number of collections, possibly lasting for the whole run of the application, they don't need to be traversed they don't need to be traversed for each garbage collection, which is nice. And the older generations can then be collected much less frequently. And it's also stopped the world, which is quite obvious what that means. So it just blocks the application running while it's doing a garbage collection. And this is why we were seeing those spikes in the latency profile and those pauses in the thread scope as well. So this is the worst case for our message store, and I'm going to explain why that is. So in our store, the objects have long and equal lifetimes. So this breaks the most objects die young assumption, and it basically means that the generational system is redundant, because all the objects will just end up in the old generation straight away. There's also, so normally the assumption is that the old generation is going to be holding long-lived objects which are going to be referenced for a very long time, probably the whole run of the program. Whereas in our case, we've got a very large old generation, and there's going to be a lot of unreferencing going on. So this means that there's going to be frequent long collections. So this is just a sort of to illustrate that a bit better. So GHC's garbage collector is really good when there's a small working set for each heap, for each generation, and it's even good when there's a very high rate of unreferencing. It can also be good when the old generation is small, but we had an old generation which is large and this high rate of unreferencing. So the slow frequent collections plus stop the world is what was causing our latency spikes. So we had a couple of solutions: either rewrite the store in C or rewrite the program in another language, and we ended up rewriting it in Go, which is a little bit sad, but it did solve our problem. So I thought it'd be interesting just to compare some of the design decisions in Go's garbage collector with what's done in Haskell, GHC. I should say why Go in the first place. One of the big reasons was it already has production raft library, so that just makes sense to use it really. But also, so it's garbage collected, but the garbage collector, they specifically have really tuned it for latency, which is obviously good for our use case. And so this is the kind of stuff we're looking at when we're investigating different languages. This is kind of proving that point that they're making a lot of progress in terms of worst case latencies. We're now on Go 1.7, and I mean it's kind of impossible to see at the scale they've used here. This is more just to show the general improvement as versions increase. And actually Go 1.7 now is much better worst case latencies. But if you compare that to what I showed you previously, so 1 million messages is about a gigabyte, so it's a similar-ish scale to that. You can see the Haskell GHC garbage collectors kind of similar to the older versions of Go. And so those yellow dots were very appealing to us. And they also show in the same presentation, there's unfortunately the scale here is completely different, and the horizontal axis is much less than the previous slide, but you can see that it keeps very, very good worst case latencies, and you could kind of extrapolate that out to the sort of numbers that we were seeing there. So how does it achieve lower latency? It's based on tricolor mark and sweep, which is quite a simple algorithm. Unfortunately, they don't really go into the details about how it works, unlike GHC's one. But it's basically so tricolor mark and sweep is basically like mark and sweep, but it's, I'm not going to go into the details, but it's easier to make phases of it concurrent. So most of the phases are run concurrently, so for each collection, about 80% of the time is running concurrently with the mutator, which is how it achieves these like very small pauses. Yeah, I put that link there. It's not all roses. This is a blog post by Twitch, and they basically showed that for unfortunately they don't say how much data they're dealing with, like the size of the working set, but they have quite bad latencies, and they do show that as the versions have got better and the garbage collectors got better, they've got actually, it's kind of removed most of their issues that they were having with Go 1.5, I think. So GHC does actually have something similar, where you can optionally turn on a compacting algorithm in the old generation, and it's similar to so it's another in-place collection algorithm. But yeah, we didn't really find it to particularly help us. We thought maybe it would help because while you still need to do a traversal of all the objects, maybe it was the rewriting of the pointers, which was expensive, and you may not need to do that as much with these in-place garbage collectors, but we found the running time to be roughly the same as with the default one. And it doesn't seem to be used very much, so it could just be general immaturity with it. So I just thought, just to contrast my pros and cons of Haskell, just some of my thoughts on Go after using it for 3 months now. I do miss a lot of what's in Haskell, so the type system, the syntax, that sort of thing. And there's also, so I appreciate that Go strives to be a simple language that's easy to learn, which I do really like. But I think there's some things that Haskell has, like sum types, which I don't think they're a particularly hard concept to get your head around, but they really help in terms of just defining or help provide correctness guarantees, stop various runtime errors. So I just think things like that make sense. But overall, I do enjoy it. It's very easy to pick up and be productive in. And I also like the fact that there's, even though it makes me a bit sad that a lot of things are just baked into the language as special cases, it is much easier in terms of the error messages and that kind of thing, which is what I showed in Haskell. Michael Walker was on our team as well, working on the Go version, but he's a Haskell guy as well, and he wrote up some of his thoughts on this, which I think are quite good. And he's a bit more on the negative towards Go side and positive towards Haskell side. So just to get a bit of contrast, it's worth reading. So this is actually now running in production, so that's obviously something to be said for the Go version. And I just thought we could look at directions the GHC garbage collector could go in that would make it more effective at our particular use case. So there's this email here from 2010 where someone wants to implement a real-time system, and Simon Marlowe wrote up some of his ideas on it, and he basically says that his main focus at the time was working on thread local heaps, which are basically an optimization where each thread has its own heap that it just collects independently. But this was only for the young generation, so it wouldn't really help us anyway. And as it turns out, it never quite got to the maturity where it could be merged into the mainline. But he does mention that, so the two approaches would be to either do an incremental garbage collection, which is where you don't, for each run of the garbage collector, you don't need to do an entire traversal of the heap. You can stop and then restart sometime later. So this lets you bound the running time of each collection. And also, it could be made concurrent, like Go, but he says that just given the existing design, it'd be very, very hard to retrofit it with these kinds of things. Having said that, so on the Stack Overflow answer that he's provided, there's this thing called compact regions, which I think might make it into GHC 8.2. And it's basically, I'm not particularly aware of the details, but it's a way of having a special data type that doesn't need to be traversed when you do a collection, which looks really interesting. And I think that sounds, in theory, like it would solve our problem if we use that for the storage, the message store. And this recently on the GHC wiki, there's a thing called linear types, which I don't know much about at all, but on the page it says that one application of them is it lets you do type-safe manual memory management. So that also could potentially be interesting, but I think that's very sort of early days, to be honest. So following on from that blog post that I mentioned my colleague James did on investigating these issues, this guy called Gabriel Scherer did some work on basically implementing the same minimal test case that reproduces the problem in OCaml and also Racket. And I think Racket wasn't too impressive, but OCaml showed really promising times. So for 200,000 messages, it's getting like 2 millisecond worst case pauses, which was quite impressive. And the way I understand it, I don't know much about the OCaml GC at all, but it uses like an in-place collector in the old generation, a bit like Go's one. So it shows that it can be done in quite a similar language. Yeah.
When you say an in-place collection, you mean that it doesn't copy?
Yeah, yeah. So some kind of compact mark and sweep or compacting algorithm. Yeah.
It's running concurrently.
Sorry. Sorry.
So if it compiles, how can it compile without copying?
So it does do some copying. Yeah, it will be doing some copying, but it depends on the specific implementation. It might just start freeing individual objects, and then at some point it might do a compaction, but it doesn't always copy. I think that's the idea. Not an expert though. So yeah.
So is this running concurrently?
That's the impression I get. Yes, but I'm not. Don't quote me on that. I think that's the idea. Yeah. So yeah, I'm kind of wrapping up really. I do just want to say thanks to Simon Marlowe for putting us out of our misery slightly with this. And also WellType did some work with us on the initial implementation of the message store. So basically, in conclusion, I think Haskell is still a great, awesome language, and for most use cases, I would like to use it again. But I just think for real-time systems, if you've got hard real-time requirements, then just think hard about that. So basically, if you've got a big, large working set in memory and have real-time requirements, then it might not be the best choice unless you want to deal with like the foreign function interface and maintaining a C code base. So yeah, hopefully just talking about it and blogging about it and everything like that, it will might promote improvements in this area, and I think the future looks quite bright for this similar use cases that we're using it for. And that is it. Thank you very much. So yeah.
So what was the number of lines, code lines involved? And were they the same? Did they do the same stuff? The implementation was the
Oh,
same?
that's interesting. So yeah, they were feature-wise
compatible, yeah.
basically the same. Yeah, it's a bit unfair because we wrote our own Raft implementation, which we had kind of factored out into a library, but the interface wasn't that nice. So there's still some logic in the.
So for a rough like-for-like comparison.
To be honest, I think it was pretty similar. I don't know the exact numbers, but it felt about the same. I think because it was quite an I/O heavy code base, so you don't get the sort of. There's a lot of just like almost all of it was just like do blocks and a lot of. So it wasn't that different. Yeah, I don't know. Maybe it's like 2/3 the size of the Go one, the Haskell version, for the same thing. Any more? Yeah.
It's not really a question, but just on a point of information. OCaml doesn't really have a multi-processing story, so it's unfair. So that 2 milliseconds might not be a apples to apples comparison.
Interesting. Okay.
I have a question.
Yeah. Okay. Yeah.
Just in terms of the concurrency, do you think it would be possible to have a fully concurrent sort of, something that doesn't pause ever?
Yeah.
Runs in the background.
Yeah. So that, according to the Go people, that is possible. So I was reading about they basically make the trade-off that apparently it can be done with tricolor mark and sweep, but there's an invariant. It's a bit complicated to explain, but there's basically an invariant that you always need to maintain, and you can do that concurrently, but it's quite expensive and really complicated to implement. But it can be done.
Expensive in terms of what?
Sorry?
Expensive in terms of memory, CPU? What?
I think CPU. I'm assuming. Yeah.
Is there any overhead for non-garbage collect when you're running code that isn't garbage collecting? If you're using the tricolor, I don't know how it works, Claude.
So
does the garbage collect algorithm have any impact on the non-garbage when you're running non-garbage, as in when you're not garbage collecting? Is there performance degradation?
I don't think so. No, I think it just when it runs.
Separate, right?
Yeah, when it's like the Haskell will periodically run. So no.
The follow-up question I had is looking at that Fresco graph.
Yeah.
It looked about 10% of the overhead with garbage collection.
Yeah.
There were these pauses that were about 10% of the total
Yeah.
time. How much bigger do you reckon the overhead would be with that kind of concurrent? Because I mean, with your app, it probably wouldn't matter if it was 30 or 40%.
Yeah.
Even if you spent half its time garbage collecting in the background, you wouldn't care because it's still responsive.
Yeah.
So,
Yeah.
Do you have?
I would have no idea, I'm afraid. But it's an interesting point. Yeah, for us, we just spend more money on bigger machines and deal with the fact that it's costing us more CPU time. But yeah, I'm not sure. I'm not sure about that.
I guess the other question, you didn't really touch on it. Bigger machines or more machines? Because if you've got RAF, you must have multiple machines in there somewhere.
Yeah.
See where they go. Is it just to scale out?
So
smear the queue across it.
Yeah, so the idea, basically we do something called multi-raft, where you can have, so each machine will run a number of instances of raft, and then you can have, so you'll have something like 64 instances of raft, and a number of machines, and each machine will be managing a subset of those raft instances. So that lets you do quite easy horizontal scaling. So yeah, you just add more machines. Yep.
Are you going to have any more Haskell in production?
I'm worried that might be the nail in the coffin, just in terms of, I think it's a mixture between, I think people do still like Haskell a lot, but I think people like the fact that you can get stuff done in Go very quickly. It can sometimes be quite unpleasant at times, but you can make do with it and it gets the job done. And yeah, we'll see. I don't think so. Yeah.
So when you were considering languages, you were getting off Haskell, considering Go, did you consider any other languages? For example, Rust or Erlang or something like that? So
not really, and the reason is because Go has the Raft libraries, so it's kind of the combination of the two things. But something like, OCaml was the fact that it doesn't have this good concurrency story was quite off-putting to us, but even Rust as well, from what I understand, it's still quite low level in terms of the concurrency. Something like Erlang could have been a good fit, but yeah, I didn't really look too much into that.
I think Erlang's very good.
Yeah, I think in general, just for not even this system, but just in general for our products, it sounds like it would be a good fit for us. We have done some experimentation with Elixir, but we still haven't. No one has any experience with it, so it's quite a big step to adopt that. Yep.
Did you try implementing message store in another language? I think you mentioned C.
We did. So we did actually write a version C, like quite a toy version, but like a feature-complete toy version. But I think we just got to the point where, none of us are particularly experts in C, and also just the thought of maintaining these two code bases, and the Haskell foreign function interface is quite unpleasant. Like it's very, very low level and just really like it's all the stuff that's nice about Haskell. You kind of lose all that when you go to working with the foreign function interface. So, yeah.
Did you try benchmarking that?
Yes, yeah, we did, and it seemed good. It basically removed our problem because we're doing all the memory management ourselves. So, yeah.
Why do you have to linearize all of your messages through one system? Is that is this for understanding how the system works, or because like the whole idea of using Raft or Paxos is you have because you don't want multiple serializations of the events because you have causal, is there any causal stuff, or is it just
but what our customers get is the idea of channels, and we guarantee that within a channel all the messages will be ordered.
But why do you need a globe? Like, are these channels quite, what do you call, can't you have a partial ordering so that like between the channels you don't care?
Yes, but yeah, that's true, yes. So you kind of get implicit sharding in the
volume.
Sorry?
Do you have a lot of volume in an individual channel?
We have a kind of, if you graphed the volume per channel, it'd be a small number of very high volume ones, and then like a long tail of much smaller ones. So that, I guess that is the issue, is the larger volume channels.
And did you try other data structures rather than binary search trees when it comes to your map data structure?
So basically we wanted to support efficient inserting, and then also looking up a range of messages from a given ID, and then also, so that's within a channel, and then we also wanted to limit, so we have, the customer has multiple apps, and then each app has multiple channels, and we wanted to apply limits on the customer's app as well. So we needed an efficient way of indexing by app. And then also we wanted to do like a global expiring as well by time. So we just found that basically using priority queues to index into this data structure was the most efficient way. You basically get log n lookup time for all of those operations. Okay. Yep.
Again, related to what others were saying about Raft, just to make sure that's not the case, was it possible, would it be possible to split up sharding the storage for a single channel, or it was?
You mean use multiple instances of Raft for one channel?
Yes. I don't know if it makes sense.
No, not really, because that is what Raft's giving you, is that, well, you won't lose messages, and you also get this guaranteed ordering as well.
Okay, that was the question.
Okay, yeah. Any more? Yep.
Does Kafka not give you what you need?
Yes, it does, but no. So the main problem with it is, so Kafka has topics, which are like our channels, and from what I understand, so Kafka was looked at before I got involved in the project, but from what I understand, so we let customers create channels lazily, so they just publish a message and that creates a channel. But in Kafka, it's more of you can create them dynamically, but it's like quite an expensive operation, from what I understand. So that was basically the main reason for not using it.
I assume that when you wrote the Go version, you pretty much kind of transcribed the Haskell version.
It was similar architecture, yeah.
Did you find there was anything that you struggled to translate? I mean, there were lots of things you would have missed, but kind of things that literally you couldn't write. You had to kind of redesign it.
I'll say probably not really. So we were basically just, most of it was just a number of threads which communicated with STM queues, and that is what you get. That is just how you do concurrency in Go. So it was quite similar, really.
Did you manage to, did any bugs sneak in because it wasn't, because you kind of broke the tops out?
Yeah, probably. Yeah, I'm sure. Yeah, I'm sure there's quite a few bugs that we were Go specific and wouldn't have happened in Haskell. Yeah. just have to write more tests.
Well, if there are no more questions, I think we should thank Will again.
Thanks.